Welcome to the inorganic course. Today we'll be looking at group 1, the alkali metals. So to start with, we can have a look. The lesson objectives will be to understand why, if you're in the same group, you have the same chemical properties. And that is because your outer number of electrons are going to be the same. And the metals always lose electrons, so it will be all about the way they lose their electrons. Then we're going to look at what observations you can make when a group 1 metal is put in water. And we're going to look at explaining and justifying the trend that you see. As a quick starter, there are here some questions. So what group is carbon in? You would have to look for it. Group 4. What period is aluminium in? Period 3. How many electrons are in lithium? 3. How is the modern periodic table arranged? Increasing atomic number. Why do elements in the same group have similar chemical properties? Well, we've been over this. The same number of outer electrons, number of protons plus neutrons. And this will be 19 minus 9, which is 10 neutrons. Right. So the first thing is, what happens when a metal reacts with water? You need to know that it forms a metal hydroxide plus hydrogen. The only condition is that the metal has to be more reactive than hydrogen for this to work. So it essentially displaces one of the H's from the water. Now, group 1 metals have one electron in the outer shell, so when they lose it, they'll always form a +1 ion. Why are they called alkaline? Well, it's because they make metal hydroxides, and OH minus, the hydroxide ion, is what makes an alkali. So the reaction you have is here. If you just ignore the question mark and turn it into an arrow, then this is like a generic way that you can balance any group 1 metal. So the capital M represents any group 1 metal, which is a solid. You drop it in the water, which is a liquid. Arrow. It makes a metal hydroxide. Now, if it's in group 1, then +1 and OH minus 1, which is -1, they cancel to make, for example, KOH, NaOH, LiOH. So the M represents any group 1 metal. That will be aqueous. The metal has actually disappeared because it has turned into a solution. So then the last point is hydrogen gas is H2, which is just a gas. So with the state symbols, you can already see two of the observations. There will be fizzing or effervescence because of the hydrogen gas, and also the metal will appear to disappear. Now, I'm going to go over the main observations for lithium, sodium, and potassium in terms of how easy it is to cut, how the surface looks, what happens when you put it in water, and is there a flame? So in order to do this, I'm actually going to go to a white document, white piece of paper, and show this to you the old-fashioned way. So let's start with the one at the top of the group, lithium. Don't know what happened here. Let's start with lithium. Lithium. Okay, these are observations of group 1 metals with water. What happens when you drop them in water? Now, when you drop lithium in water, it will fizz. Fizzing / effervescence. Okay, it will disappear / dissolve. It will float. It doesn't sink. It is less dense than the water. It will move around. Now, these 4 observations will actually occur for sodium and potassium, and all of them essentially. They will all do these core basics. Okay, so if you copy and paste that technically, and paste it one more time, they will all do these things. It's just that as you go from left to right this way, everything will become more vigorous or violent. I've seen recent mark schemes, they prefer violent to vigorous. So it'll fizz more, it will move around more. Now, there will be additional observations for some of these. By the way, they actually all have a fact that they release heat. They're all exothermic, but that's not something you can normally see with your eyes. So for now, I'm going to leave these as the core ones. In terms of how easy it is to cut, this one is, lithium is actually the hardest one to cut. So it's the hardest to cut. And when you cut it, it is shiny, but slowly turns dull. Okay, this one will be the easiest to cut. And instantly turns dull. Okay, starting from shiny. Now, the extra observations for sodium would be it turns into a white ball and it leaves a white trail, but there is no flames. And the special thing potassium does is it is so violent that it forms a lilac flame. Okay, note all are exothermic and release heat. It's just that you can't see the heat. You might see some steaming. Also note that all stored in oil to prevent reaction with air, which has oxygen, so vapor. So some of the safety precautions taken would be, well, one more note here. Note, if universal indicator is used, it will turn from being green in water to purple due to the hydroxide ions. And for safety purposes, you need to know, you wear gloves because you don't want your hands to touch because they might be wet. Forceps, goggles, small pieces are used, otherwise it'll be too violent. And a big trough of water with thick glass sides so that the heat can dissipate and it will not shatter. So that is the main point. I like to say fizz, float, move, dissolve. That's what they all do. So these are easy marks that you can just generate in an example. It's all written in my answers. So my common questions and answer sheet. If I load that up, it will have a section on this. Very simply put, and all we're doing today is going to be covered in here. So fizz, float, move, dissolve, release heat and form alkaline solutions. Sodium melts into a white ball and leaves a white trail. Potassium produces a lilac flame, has a more vigorous, violent reaction. Everything is here. The only thing we haven't done is what happens when you go down the group to explain it. Now, one thing that should also be mentioned is the metals can react with oxygen as well. So if I go back to my PowerPoint, I can find it. There it is. You should also note that we play this. So when sodium reacts with oxygen, it forms sodium oxide. So the group 1 metal will form M2O because the oxide ion is 2- and the sodium is +1. They'll all be exothermic reactions. So they're all shiny when they're freshly cut, but they quickly react with the oxygen and they tarnish or they turn dull. When they form the sodium oxide, they form a white solid, which appears as a white smoke. And that's because the solid gets vaporized, turned into a gas by the large amounts of heat released by the reaction. You may also see now different colored flames here. So for the sodium one, you might see a yellow flame. So I have seen exam questions on this. You would just say a white solid is formed and there's a flame. They could also be used to react with chlorine as well. Okay. And in the same way as with oxygen or with water, you can see which one is the most vigorous reaction. So this is another example. Sodium plus chlorine makes sodium chloride. Sodium chloride is also a white solid. And the sodium will burn in the chlorine with an orange flame. I think I said a yellow flame. It's orange. It's more orange, yellow-orange. If you put the white solid in water, it will dissolve, form a colorless solution. That's what all group 1 metals do. Okay, next we can look at their trend in melting and boiling point. So this is an interesting point. So I'm afraid the font hasn't come out very good, so I'm just going to go like this, try and sort this out. This is rubidium. This is cesium, supposed to be. Sodium, lithium, sodium, potassium, rubidium, cesium. The numbers have a little bit overlapped, unfortunately. So the main point is what you have here. I'm going to copy this and put it into a new slide. Where are we? If I put a new slide here, I can just paste it in here. And then just see what happened. So the melting and boiling points decrease down group 1 because the atom gets larger. So if you remember metallic bonding, we have cations with a sea of delocalized electrons outside. So if the cation gets bigger, its attraction to the outer electron will get weaker. So less energy will be required to break these attractions. That's what this says. And therefore, it'll be harder for it to melt or boil. So this is the complete correct font. Okay. So melting and boiling points decrease down group 1. You should remember that. Group 7 does the opposite. So it is something to be aware of. So what I was saying was, if you have a cation here, if I draw your cation with a negative electron on the outside. Now, if I draw a bigger cation with a negative electron, then this will have a weaker attraction from its nucleus than this. So as you go down the group, they get bigger. So therefore, the attractions of the metallic bonds get weaker. Now comes the most important element of all this, and that is to explain the reactivity down the group. Why do they get more reactive down group 1? It is a similar principle to this, but not quite the same. Let's have a look. It is this slide over here. I'm just going to fix this font here, and everything will look nice. There we go. Okay. So if we play this slide, this is very good. So you can see here the metals from top to bottom, lithium, sodium, potassium, and you can see that blue outer electron, the valence electron. The ultimate objective is for that electron to be lost. So which one is going to lose it the easiest? The answer is potassium. Because if you imagine that center circle, the yellow circle, has the nucleus with the protons, which are positive, that's going to form a nuclear attraction to that outer electron. The stronger that attraction is, the harder it is to remove the electron. So lithium would have the strongest attraction because the nucleus is closest to the outer electron. The way you put this into words is that the atomic radius increases down the group. So just like a radius of a circle, the outer electron gets further away from the nucleus, and there is more shells and more shielding. I call it a double shush. More shells, more shielding. So shielding is a term used to describe when the shells are repelling each other because they're negative. So they're causing a repulsion. So obviously, the more shells you have, the more they can repel each other. Furthermore, it's called shielding because the nucleus is positive, but the electrons are around it. So the nucleus is being shielded by these shells. Okay, that's where the term comes from. So as I said, this creates a weaker nuclear attraction between the outer electron and the positive nucleus. So it takes less energy for the electron to be removed, or you can say it's easier for it to be removed. In more recent mark schemes, they prefer less energy to be removed. And that's why the reactivity increases down group 1. I shall attach this PowerPoint anyway. Now, This is the bit in bold for Edexcel people. This will be in the paper too. For AQA, this is just normal stuff. Now, there's one finer point. If you think about it, as you go down the group, the number of protons rapidly increase. So for example, lithium has 3, sodium has 11, and potassium has 19. So some people might say, well, hang on, more protons means stronger attraction. However, they'll be wrong, because that the nuclear charge is cancelled out, or not cancelled, but overpowered or outweighed by the shielding effect of the shells repelling. So the increased nuclear charge, i.e. more protons means more nuclear charge, it is outweighed by increased shielding. And that is the final point on group 1 metals. So just learn the facts well. Everything is in your notes for you to see. I'll save this and attach it for you. Then in my common questions and answers, you can clearly see more reactive, more shells, more shielding, weaker nuclear attraction, less energy to lose an electron. Everything is here. So that's the end of group 1. And it's not the hardest topic if you learn your stuff. I will see you next time for the group 7 lesson.